Many scientists have argued that human cloning technology is absolutely vital to the future of medical progress, and that without it we will not be able to find the cures that we need for things like multiple sclerosis or Parkinson's disease. But are scientists actually right? Probably not. And that may be one of the reasons why human cloning technology has not attracted much research funding over the last few years. Almost all of it has been going into straightforward embryonic stem cell research, and from there it's been shifting into research using adult stem cells. Embryonic stem cells are those taken from an embryo in the early stages. These cells are omnipotent. They are able to give rise to just about everything you could possibly want and more. The problem is controlling them, as they are set for vigorous growth and can easily develop into cancers, creating all kinds of problems. The other problem is rejection, because the cells themselves are not identical genetically to the adult who may need them. Then along comes a separate kind of technology using adult stem cells. Now, in the past we thought that adult cells were almost all determined. They were fixed, that certain genes were fully turned off, and that would be the case until the day that you died. That it would be impossible, for instance, to persuade a bone marrow cell to become a useful tissue as a component part of, say, heart muscle or brain tissue, or to help repair the spinal cord. We now know that that's not the case, that there are cells in many different tissues which have the capacity to convert into other kinds of tissues, or perhaps not convert directly, but to produce substances which themselves accelerate healing or local organ regeneration. Now, we see this quite routinely now. We've seen a woman who was found to have male cells inside of her brain after she died. These were presumed to have arisen from the male bone marrow transplant that she received as part of her cancer therapy some years previously. We've seen other examples where bone marrow cells have been able to form a useful component part of the healing process of heart muscle. We're not sure exactly how this happens, but we're seeing an explosion of research studies suggesting all kinds of really exciting things are possible using these adult cells. We've seen partial repair of spinal cord in animals. We've seen repair of brain tissue that's been damaged after animals have had strokes. There are other scientists who are working on rebuilding the light-sensitive part of the eye, retinal cells. These cells are damaged in things called macular degeneration, which is a common disease of those who are old in America, Europe, and just about everywhere else. Scientists are using these kinds of cells in animal studies to regrow the retina, and these retinal cells, which are derived from either embryonic stem cells or in some studies from adult stem cells, they reattach themselves to the optic nerve so that the animal regains partial sight. These are spectacular advances that would have been considered to be totally science fiction even as recently as 1999 or 2000. And we can expect further progress here. And all this is leaving the human cloning industry looking rather last century. Because what research scientist will want to take money to do work where he could land up in prison doing that work in many countries, using embryonic stem cells or cloning human embryos, when you have the chance of doing almost exactly the same kind of thing using adult cells taken from the person's own body, which can be put back into the person's own body without any risk of rejection or just about any other problem. So expect to see further dramatic improvements in adult stem cell technology. Now, there are those that sit on the backside here and say, well, you know, it's all very well, Patrick, but it's rather theoretical, and that we don't see it happening, or it's quite difficult, or there's a lot of hype about adult stem cells, and we really think the action is in embryonic stem cells. Well, that's true, that's still the case, but as I say, watch out, the situation is changing. And even a moment's thought tells you why it should be so. The only real difference between an embryonic stem cell and an adult stem cell, as we have seen, is which genes are active in that particular nucleus. And as we've seen from adult cloning technology, when you take an adult nucleus where most of the genes are turned off and you pop it inside the chemical bath of an egg, then straight away all of those genes, or many of them, are activated in a way which will give rise to an identical clone of that original individual. Now, once you understand that, you begin to see that the whole trick in terms of converting, say, an adult skin cell into something that's more flexible, or all the way back towards something which looks and behaves like a human egg, it's all to do with the chemical messages around the nucleus. And that, once you've realized that, is a tremendous open door for new advances in science. Because if you can find what those chemical messages are, then perhaps you don't need an egg in order to produce a clone of someone. You could just go straight, in theory, from a skin cell to a skin cell plus the chemical bath to a skin cell which is now fully activated and ready to become a clone of an adult. Now, what is missing, of course, is the large cytoplasm around that nucleus, which gives the cell the energy to form its initial ball of cells and get ready to implant, and before it can get its nutrients for the future through the placenta from the mother. But nevertheless, it's an interesting thought. And that's exactly what scientists claim to have done recently with various tissues, where they've got the cell, found the chemical triggers, and seen it regress. And many scientists have done this in different ways with different results. And different cells only need to be regressed a certain amount in order to go off another path. Other cells need to be regressed much more substantially. An example is liver and pancreas, which in embryology terms, in development terms, they arise from a very similar part of the embryo and the fetus. And people like Professor Jonathan Slack at Bath University some years ago have shown that with certain chemical triggers, you don't need to do too much in a liver cell to activate genes which turn that cell effectively into an insulin-producing pancreatic cell. And he's done this in tadpoles, and he's been experimenting and doing this with human liver cells. Fascinating. So we're partially regressing a cell and then pushing it up another path without taking it all the way back to the embryonic stage. But as I say, you're going to see and hear an awful lot more about this. And in the process, the human cloners, those who are wanting to do it for research purposes, will find themselves, I think, looking more and more last century. What will we be left with? We'll be left with a few people who are still trying to use human cloning technology to do what some pet owners are doing and try to duplicate existing human beings or people who are dead. Dead? Could it be done? Well, yes. I mean, Dolly was cloned using frozen tissue. Dolly's mother was dead long before Dolly was even created. So in theory, we already have the technology to produce a new human being who is an identical twin as someone who died many years ago, whose cells have been perfectly preserved through a special technique in a frozen state. But that is the future. The thing about the future is this: not everything that can be done will be done, and not everything that will be done should be done. Either we take hold of the future, or the future will take hold of us. Either we have these debates now about how science should be used so that society has a chance to come to terms with what it wants for the future and can regulate and bring a big debate about the progress that they want to see, or we will find these things are foisted on us by one announcement in the newspapers after another. And by the way, not everything that is being done is being published. For a long time now, there's been a significant gap in some laboratories between what some scientists have felt comfortable about publishing and what they haven't. And one of the reasons is that there's quite often a large emotional reaction within the public, which they fear, and that is why some results have been kept back. Dolly the sheep was an interesting case in point. Dolly was already several months old before the world was told that she'd been born. But Dolly had been made several months before she had been born in the first place, and the research itself was well underway months and months before that. So why the gap? Several reasons. One was to register patents. The other was to be sure that the technology had actually worked and that Dolly was healthy, and so on. But what I'm saying is, The headlines are often a long way behind the reality.